Warahmatullahi wabarakatuh. My name is Muhammad Azizi Aswad and my metric number is DE18017. Okay, now I'm going to explain about my FYP2 project, the development of dual switches bridgeless power factor correction totem pole Sepic converter for LED driver application. Okay, there is five content of this presentation. Okay, the first one is project background, problem statement, methodology, result and discussion, and finally the conclusion. Okay, for the project background. Okay, what is BPFC totem pole circuit? Okay, the bridgeless power factor correction single-ended primary inductor converter is integration between the AC DC rectifier and the DC DC converter that use totem pole circuit structure that can improve the THDI and power factor and output voltage ripple. Okay, the problem segment is for the power quality issue is such as high THDI. Okay, as you can see at the top of the picture is before optimization 9.4% the THDI, and after optimization is 4.0, the THDI is 4.0. Okay, according to the IEC standard, the standard of the THDI is below 5%. Okay, next, the issue is the power quality issue such as high output versus ripple. Okay, as you can see before the optimization, the ripple is high, and after optimization, the ripple is low. There is three main objectives in this research. Okay, the first one is to design the bridgeless Sepic converter using the single phase totem pole PFC, TP-PFC for THDI and power factor improvement. Okay, second, to analyze the output voltage ripple on the single phase BPFC totem pole Sepic converter, and finally to develop the hardware of BPFC totem pole Sepic converter for parameters comparison with the ideal case and the circuit model based on the actual parasitic component model simulation. Okay, next, for scope of this project, okay, the first one is Plex software is used as the simulation software. The second one is switching frequency for the BPFC totem pole Sepic converter is 10 kHz, and the MOSFET is selected as the switching devices for the simulation and the prototype. Okay, next, the field programmable gate array FPGA Altera DE270 board controller is used to provide signal pulse width modulation PWM. Okay, for 0.1 duty cycle is selected for the theoretical verification, simulation, and the prototype. And finally, next, the RMS voltage of the AC source is 110 volt until 230 volt in range, and the output power is range between 23 watt to 14 watt, and the output voltage DC is fixed to 48 volt for the calculation, simulation, and prototype purposes. Okay, 6, the Intentional Electrotechnical Commission IEC SIG 10032 standard to ensure the THDI of the structure follow the standard. Okay, 7, optimization of parameters design of BPFC totem pole Sepic converter is carried out to reduce the THDI, power factor correction, and reduce output voltage ripple. Okay, next, related issue in designing the BPFC totem pole Sepic converter. First, to reduce the THDI and improving the power factor. Second, to reduce the output voltage ripple, and finally the efficiency. Okay, to reduce the THDI and improving the power factor is we can optimize the circuit structure and parameter design, and for the output voltage ripple is using the higher output capacitor, and finally for efficiency we optimize the circuit structure and the parameter design. Okay, for the methodology, okay, this is the BPFC totem pole Sepic structure. There is 4 sides. The first side is boost side, and the second side is totem pole bridgeless side, and the next is the back side, and finally the output filter side. Okay, for the why this structure is called the totem pole, because it using only two switches and two diode. Okay, so as we can see here, the totem pole bridgeless side is contained with two diode and two switches here at the middle of the converter. Okay, next. This is the waveform of bridgeless totem pole Sepic converter. Okay, there is 4 mode in this one. For when the time is on, when the switch is on, it's going to be in the mode 1, and when the switch is off, it goes to mode 3, mode 2, 3, and 4. Okay, on the left side is for positive cycle, and the right side is for the negative cycle. Okay, result and discussion. This is the BPFC to Tompo Sepic circuit structure that I run through the Plex application. Next, this is the BPFC to Tompo Sepic circuit structure that I run using the hardware. Okay, the first one, we have the FPGA. Second one, we have the power supply for gate driver unit. Then we goes to the gate driver unit, and finally we goes to the BPFC totem pole separate converter circuit. Okay, we use the oscilloscope to record the result of the output, and we use the AC source power supply to supply the BPFC totem pole separate converter circuit. Okay, this one is the load with 100 ohm based on the THDI result. Based on the simulation THDI result. Okay, this is THDI for 4. The THDI for the result for 100 ohm is 4.5%. We got, so it according to the IEC standard. Then for the experimental, we got 24%. This is due to the this is due to the internal inductance at the output resistor load. This result we record using power analyzer. Then this is power factor from the experiment for 100 ohm. Okay, the power factor we got is 0.451. Okay, this is the load with 120 ohm based on the simulation THDI result. Okay, the THDI is 4.2%, less than when the load is 100 ohm. Okay, next for the experimental THDI result for 120 ohm is we got 23.9%. Then for the power factor we got 0.415. And for the power factor we got 0.415%. Okay, next we got for the load with 140 based on simulation THDI result, we got the THDI is 4.0%. And for the load 140 we got from the power analyzer we got 23.8%. And for the power factor we got 0.393. For the load with 160 ohm, we got the THDI is 3.8%. For the THDI from power analyzer 23.5%. And finally for the power factor we got 0.384. Then next I want to explain about my second experiment, that is high output voltage ripple with capacitance 470 microfarad in the simulation. Okay, for the simulation we got 2.14 volt for the output voltage ripple, and in hardware we got 4.40 volt for the output voltage ripple. Okay, for the 3000 microfarad capacitance, we got the output voltage ripple is 0.37, and for the hardware we got 2 volt. So finally is the conclusion. Okay, this is the THDI comparison between the circuit model based on parasitic component model simulation and the experimental. As you can see, for the THDI simulation, we got 4.5% for 100 ohm, and for 120 ohm we got 4.2%, and for 140 ohm we got 4%, and finally for 160 ohm we got 3.8%. And for the experimental we got 24% for 100 ohm, and for 120 ohm we got 23.9%. For 140 ohm we got 23.8%, and finally for 160 ohm we got 23.5%. According to this chart, we can conclude that the experiment is succeed for the first objective, and the higher the output resistor, the lower the THDI from the simulation and the experimental. Okay, this one is the graph for power factor. Firstly, 400 ohm we got 0.451. For 120 ohm we got 0.4415. 440 ohm we got 0.393, and for 160 ohm we got 0.384. Okay, according to this graph, we can conclude that the lower the output resistor load, the higher the better the power factor. Next, for the output voltage ripple comparison, we got from the simulation and the experimental. Okay, from the simulation, we can see that for 470 microfarad, for the simulation, we got 2.14. And for the experimental, we got 4.4 volt. As you can see, we can conclude that the for 470 microfarad is less 2 than in the experimental, and for the simulation we get 0.37, and experimental we get 2. This is for 3000 microfarad. So we can conclude that here, the higher the output capacitor, the lower the output voltage ripple for this circuit. Okay, next, this is the final conclusion. We want to compare the efficiency between the circuit model based on actual capacitor component model simulation and experimental and ideal case simulation. Okay, there's three comparison: ideal case simulation, real case simulation, and the experimental. For the ideal case simulation, we can see the efficiency is almost 100 for all resistor load output. And for the real case, we can see that the for 100 ohm, we can see that the efficiency is 40.96. For 120, we can see the efficiency is 39.87. For 140, we can see that the efficiency is 39.35. And finally, for 160, we can see 41.08. Okay, as we can see, the highest from the real case simulation, the highest efficiency is at 160 ohm. And finally, for the experimental, we can see the efficiency is 55.81 for 100 ohm. For 120 ohm, we got 56.91. And for 140 ohm, we can see the efficiency is 52.96. And finally, for 160 ohm, we can see the efficiency is 57.23%. Okay, the efficiency is decreases. The efficiency is increased according to the output resistor load in the experimental. Okay, from this one we can conclude that the efficiency from the experimental and real case is lower than the ideal case, because of, in this case, we can see that the ideal case simulation did not take the power losses, but for the real case and experimental take the power losses. And finally, you can see that this is because of the power losses that happen in the circuit. That's all for me. Thank you.